Well, to continue with our discussions on the drift flux model. So, what we had done in the till the last class was we found out how and why the drift flux is so very important, and then how to express drift flux model, and finally, I had written down two particular equations. If you observe these two equations, then you will find that here I have written down there is one particular equation which has come from the drift flux model, and the other equation which has come from the two fluid formulation, where we have neglected, or rather this particular equation we have obtained it from the two fluid formulation, neglecting wall effects under steady state conditions, or rather under steady state inertia dominant conditions. So, for that particular condition we had obtained this, and we find that this equation it expresses J21 in terms of alpha, and this is independent of the phase flow rates. Okay. It does not depend on how the two phases are behaving, it just depends upon how the two phases are distributed, what is the geometry, etc., based on which n and u infinity can be calculated, and this is one which we have obtained from the drift flux model. Naturally, two equations, two unknowns. So, therefore, we can solve them simultaneously and we can do it. Okay. Now, a better technique or a simpler thing is, instead of solving them simultaneously, if we can draw the curves resembling this particular equation, draw the curve resembling this particular equation, and naturally, the point of intersection is going to give us alpha and J21. Okay. So, what sort of curves do you expect? The curves should be something of J21 versus alpha, isn't it? Now, tell me, from the first equation what type of curve do you expect, or what type of relationship do you expect between J21 and alpha? Straight line, very correct. What will be the intercepts of the straight line? If you know the endpoints or if you know the slope, you can find out you can draw the straight line very easily. What will be the intercepts of the straight line at alpha equal to 0? So, you know at alpha equals to 0, J21 equals to J2, alpha equal to 1, do it and tell me. If alpha is equal to 1, then in that case this becomes J2 plus, I think this is minus, I have made some mistake, but let me see, maybe I have made a mistake in this particular case. Let me just check up with the PowerPoint thing. Was it plus or was it minus? This is the J2 minus, sorry. So, this is J2 minus, very sorry, minus alpha j. Okay. So, therefore, when alpha equals to 1, this becomes J2 minus j, and j is J1 plus J2. So, therefore, this becomes minus J1. So, therefore, if you plot J21 versus alpha, say from 0 to 1 if we take, then therefore, you are supposed to get straight lines depending upon the magnitude of J2 and J1, depending upon the signs of J2 minus J1. Do you understand? So, therefore, you will have different type of curves depending upon whether both J2 and J1 are positive, that means co-current upflow. Okay. Both J2 and J1 are negative, that means co-current downflow, or else one is positive, one is negative. Depending on that, you will have different curves in different particular quadrants. Now, let us see what type of curves you are going to expect and what you are going to get. Now, see, in this particular case, suppose you are having co-current upflow, that means if it is co-current upflow, J2 is positive and J1 is positive, or minus J1 is negative. Yes. So, therefore, this is the curve for co-current upflow, right. Acha, now you try to understand certain things. See, suppose your J2 is constant and J1 is increased. So, what happens? The straight lines they intersect the alpha equal to 0 axis at lower and lower values. Okay? The implications we will see later. Now, let us see if it is co-current downflow. Downflow means we have already assumed the upward direction as positive, right. So, downflow means J2 is negative, J1 is negative, or in other words J2 is negative and minus J1 is positive. So, therefore, this red colored line, this shows your co-current downflow. Do you agree with me? Okay. Now, the other thing, counter current flow. Counter current flow can be two types. One is gas up, liquid down, liquid up, gas down. Okay. When it is gas up, liquid down, then in that case what happens? J2 is positive, J1 is negative, minus J1 is positive. So, therefore, the straight line, this is the blue line which lies entirely in the first quadrant. Do you agree with me? Acha. Another counter current, gas down, liquid up. Gas down means J2 is negative, liquid up, J1 is positive, minus J1 is negative. So, therefore, this violet color line which lies in the fourth quadrant. Do you get my point? So, therefore, co-current downflow, co-current upflow, they intersect the alpha equals to, rather the x axis. Okay. That means, for the co-current upflow and co-current downflow, naturally both of them have the same sign, or in other words J2 is positive, J1 is positive, or J2 is negative, J1 is negative, as a result of which we get J2 positive minus J1 negative, co-current upflow, J2 negative minus J1 positive, co-current downflow. Agreed? So, therefore, what do we find? We find that for different particular flow situations, we can have different straight lines. Fine. Achha, this was when we plotted the first equation which I have written down in this particular case. Okay, the first equation which I have written down, for this particular equation we have obtained the graphs which, or rather the straight lines which I have shown. Now, if you plot the second equation, we will be doing problems and then you will find for the second equation, if you plot, we get a curve something of this sort. Okay. We find that the curve is something of this sort. Okay. For different values of n and alpha, we get this particular curve. Now, simultaneous solution means what? In the same graph, we are supposed to, this is slightly mistake, this should have originated from alpha equals to 0, this by mistake has been displaced slightly towards the left. So, therefore, if we on the same graph paper, if we plot this curve and if we plot the straight lines which I have shown, then the intersection of the curve and the straight line will give us a value of J21 and alpha. Yes or no? Now, let us see what we have done. This is the curve which we have got. These are the straight lines that we have got. Now, let us see. This is for co-current upflow. Okay, co-current upflow, you remember this was the straight line which we had, this was the curve which we have. So, therefore, the point of intersection, that gives you the value of alpha 0.1 in this case, and that gives you the value of J21. Fine. Notice one thing very interesting, that in this particular case you find that no matter how much J1 is increased or how much J2 is increased, you will find that always the point of intersection lies along this particular portion, or in other words it lies for a small value of alpha where bubbly flow exists. Okay, because for this particular J21, this curve we have drawn, that is for a particular u infinity and n, we have drawn it for bubbly flow pattern. Accordingly, we have selected u infinity and n. Therefore, the point of intersection should be such that it lies in the bubbly flow pattern. When does bubbly flow occur? Low gas, high liquid. So, therefore, we will always have the point of intersection on between alpha equals to 0 to alpha equals to 0.3 or something of this sort. Okay. And what next do we observe? We observe that suppose we increase J1, that means we increase the liquid flow rate. Just observe and keep J2 constant. What happens? The curve will be intersecting at lower and lower points. When this has to happen from a fixed J2, naturally we find that the point of intersection will slightly shift towards lower and lower alpha. Quite expected. Higher liquid velocities, naturally in that case we will have a lower alpha. Similarly, if we keep J1 constant, if we keep on increasing J2, what will happen? You see, in this particular case, if we keep J1 constant and we increase J2, we find that alpha shifts to higher and higher values. Quite expected. Alpha, which is the gas voidage, will increase with gas velocity, it will decrease with liquid velocity. This was the case for co-current upflow. Okay. Now, if we take the next case, very sorry. Now, if we take the next case, this was co-current downflow. Now, see the situation for co-current downflow. In this particular case, we find that more or less the point of intersection occurs somewhere here. Now, if we increase or rather we keep J2 constant, increase J1, then we find gradually alpha shifts to lower and lower values. If we keep J1 constant and increase J2, we find they shift to higher and higher values as expected. Here we find that alpha occurs at a higher gas velocity, because for co-current downflow, if gas velocity is not quite high, we cannot obtain a stable flow pattern. Okay. So, this was the point of intersection for co-current downflow. Now, let us take up counter current flow. Counter current flow with gas up, liquid down. So, therefore, gas up means J2 positive, liquid down means J1 negative minus J1 positive, right. Is this portion? It is very simple. So, it is nothing very difficult to understand. So, for this particular case, what do we find? We find that the straight line lies entirely in the first quadrant, and if you observe, you will find that the straight line cuts the curve at two particular points. Okay. If you go for lower and lower J1, we find that for every case it cuts for two particular points. Okay. If keeping J2 constant, if we keep on increasing J1 or we keep on increasing minus J1, we find finally a point comes where it just touches the curve. Under this particular situation, there is only one point of touching or intersection, whatever it is. Now, beyond that particular situation, we find that the straight line lies above the curve, there is no point of intersection. Do you get my point? So, what do you get under these particular situations? From these situations, we find that below a critical value of alpha, what do you have? You have 2 points of intersection. That means, for for counter current flow with gas up, liquid down, there can be two possible flow patterns where the flow can be stable. One is at low alpha. What does it denote? Bubbly flow, liquid higher proportion, gas lower proportion, and high alpha, sort of a droplet flow, or maybe annular type where droplets are dispersed in the gas core. Clear? So, therefore, one solution you get at a low alpha, other solution you get at a higher alpha. Clear to all of you? Now, you keep on increasing the the liquid flow rate. What happens at one, or in other words, you can also keep on increasing the gas flow rate as well, does not matter. You can keep this constant and you can keep on increasing the gas flow rate also. By any means, what you find, a point comes when the line becomes tangent to the curve. What does it denote? it denotes the limit of counter current operation. When does the limit come? Under flooding conditions. Is it clear? So, therefore, this point of tangency, this gives you the flooding condition beyond which counter current operation is not possible. So, beyond that, if we increase either of the flow rates, we find that there is no point of intersection between the straight line and the curve. So, and it is quite expected that beyond the flooding point, there is no stable operation. Either there will be a change in the flow pattern, due to which this curve is going to change, or there will be some amount of rejection of material from the flow passage. Whatever it is, the flow is not going to be stable, and or it is not going to retain the same interfacial characteristics as it had retained earlier. So, for counter current flow with gas up, liquid down, we all know that it operates within a particular stable operating range, and that range it is limited by the flooding condition at one case, the weeping condition at the other. Okay. So, therefore, below that particular, below the flooding point, we find that we can get counter current operations under two conditions. One is at low alpha, the other is at high alpha. The point at lower void fraction, that denotes the bubbly flow situation. The point at higher void fraction, it denotes the droplet flow or maybe the wispy annulus sort of flow condition. Okay. Now, when we are operating below the flooding point, we find stable operation at two values of void fraction. At the flooding point, that is denoted by the point of tangency, or the point, just the curve, rather the straight line touches the curve at one particular point. This is the point of tangency, this denotes the flooding point, this denotes the limit of counter current flow operation. Beyond this, we will not get a counter current flow operation. How do we understand it? By seeing this particular graph. If you observe this graph, we find that beyond this, the line passes above the curve, there is no point of intersection between the two. From here you get another very important thing. What is that? See, in order to generate this curve, what we had done? We had used the equation which I had already written down. I have written it down here. We had used this particular equation. Okay. Now, in order to use this particular equation, we need to know the flow pattern, we need to know u infinity and n. Now, by observing this counter current operation, what did we come to know? We have come to know that there can be an alternate way of constructing this curve. What is the alternate way? Alternate way is to construct the curve from the flooding data. If we have flooding data, then for different alpha values, there will be a different combination of gas and liquid velocities under which flooding will occur. Do you get the point? For each particular alpha, there will be one set of J2 and J1 under which flooding will occur. So, for each alpha, if we get J2 and J1, then we can construct these particular, or rather we can locate each and every point, isn't it? We will find out what is J2, we will find out minus J1, and then at that particular alpha, the point of intersection of this alpha with the straight line will give us one particular point in the curve. Thus, for the entire range of alpha, we can get the from the flooding data for different values of alpha, we can locate different points on this particular curves. And if we join the points, then in that case we can generate this particular curve from flooding data, even if we do not have an idea about the flow pattern, and even if we do not have an idea about u infinity, n, etc., etc. This can give you an alternate way of constructing this curve as well. Clear to you? Well, now let us go to the final operation. It was counter current operation with gas down, liquid up. Gas down means J2 is negative, liquid up means J1 is positive, minus J1 is negative. So, that means both J2 is negative minus J1 is negative. So, therefore, the straight line will lie in the fourth quadrant, is not it? The straight line will be something of this sort. And if you observe this particular PPT, you find that the straight line will lie here. And therefore, what do we find? For such a flow situation, there cannot be any point of intersection between this curve and the straight line. Quite expected. Have you ever found any countercurrent operation with gas down, liquid up? This cannot be a stable situation. We cannot have anything where the gas is going down and the liquid is going up. Countercurrent means gas up, liquid down. Okay? So, from this particular curve we find that such a situation is not possible, which you already know. Okay? So, from these particular curves what we have found out? From these particular curves we have found out that from the point of intersection of the straight line as well as the curve, we can superimpose them on different graphs and we can find out the corresponding value of alpha and J21 depending upon different values of phase flow rates or depending upon different values of Q1 and Q2. And what have we found out? We have found out that for co-current upflow, co-current downflow, we find that there is one particular point of intersection. Under all circumstances, this point it shifts to higher alpha when we increase J2 and we decrease J1 as expected, and the opposite behavior occurs for the if we decrease J1 and increase J2, naturally alpha increases. If we decrease J1 and increase J2, then opposite thing happens. Clear? Achha. Then we next we found out that for counter current operation, gas up, liquid down, we find either two solutions are possible. Under one particular situation, only one solution is possible. Beyond that, no solution is possible. In other words, counter current operation with gas up, liquid down can occur only under a set of conditions only. Beyond the flooding point, it is not possible. And we found out that for counter current operation with gas down, liquid up, it is never going to be possible. Agreed? So, and also from this particular curve, we had got an idea regarding an alternative way of constructing this curve, because constructing the straight lines is not a problem. We just have to know the endpoints. What are the endpoints? Here this is J2, here this is J1. What is J2? Q2 by A. We get it from the volumetric flow rate. What is J1? Q1 by A. So, Q1, Q2 are input parameters. So, from them we can find out J2, we can find out minus J1. Constructing this straight line is not at all a problem. Constructing this curve is a problem. We need to know data on u infinity and n. Apart from this particular curve, we find that if we exploit the points of tangency for different values of alpha, then we can construct this curve, okay, from flooding data. So, if we have flooding data for different values of alpha, then also this curve can be constructed from the flooding data. Now, there is one, I have a consolidated form of, just a minute. So, the entire thing I can show it in one particular curve, one particular data I have. Here I have shown the entire thing. Okay, in one particular curve I have shown the entire thing. This is for co-current downflow, this is for your counter current flow, where counter current flow with liquid down, gas up, and I have shown all the things in this particular case. Okay. After this, the next thing which I would like to show is one more thing I would like to tell you for this under this particular flow situation. Now, remember one thing, when we are doing it for gas liquid systems, more or less we find that this particular curve, it can extend from alpha equal to 0 to alpha equals to 1. Agreed? If we consider fluid particle systems, then in that case what happens is we find out that for fluid particle system we find that there is a point of discontinuity at one particular alpha. This particular curve which I have shown here, this cannot extend from alpha equal to 0 to alpha equal to 1. Can you tell me why? For gas particle system this is not a problem, but for fluid particle system we find that, sorry, gas liquid fluid systems this is not a problem, but for fluid particle system we find that there is a point of discontinuity beyond which this curve cannot exist. The curve looks something of this sort. It exists till a maximum alpha. This maximum alpha, it depends upon the nature of the fluid and the solid. If it is a flocculating solid, then the alpha maximum can be as low as 0.1. If it is totally non-flocculating, it can go to higher values. Usually for rigid incompressible particles we find that usually alpha max it varies between 0.58 to 0.62. In this particular case we have assumed alpha to be 0.6 in this particular case. Can you tell me why for gas solid cases or for fluid solid cases we cannot have the curve extending till alpha equals to 1 as we can have for gas liquid cases? Any idea of why it does not happen? Now remember one thing, the problem in this class is I cannot give you time to think. I can just throw the question and I have to tell the answer myself. That becomes a problem in this particular class. See, remember one thing, when the particles beyond a particular packing they come close to one another. When they come close to one another, particle-particle interaction becomes very, very important. Now, if you remember how we had derived this particular equation, do you remember in that case what we did? If I just go through the derivations, you will understand how did we derive this particular equation. If you notice this particular equation, what we did, first we had written it down for steady state inertia dominant conditions. Then in F1, F2 we had FW1 and FW2 and F12. Note there was no term considering F22 here, but if we have particle-particle interaction there should have been 1 plus F22 in this particular case. Is it correct? Here we have considered only, what are the cases we have considered? We have considered your interaction between phase 1 and phase 2, wall and phase 1, wall and phase 2, and then after that we have also neglected the wall term here. So, these two equations which were derived, they are just for steady state inertia dominant with the hydrodynamic drag being important, even the wall interactions are not important. And definitely in under no condition did I include F22 in this particular case. So, therefore, finally from here we got this particular expression from which I have obtained this equation. So, this particular equation was obtained under the condition of steady state inertia dominant, where absence of wall interaction effects, absence of particle-particle interaction. So, now when the particles come very close to one another, then your particle-particle interaction becomes much more important. And when it becomes important, the basic assumption on the basis of which I had derived the equation for the curve, that itself fails. So, therefore, when particles come closer to each other such that particle-particle interaction becomes comparable or more important as compared to the hydrodynamic drag, under that condition what I have to do? I have to go back to the original momentum equations, include F22 there, and then I have to do the entire derivation. In that case, the form of the equation changes, the curve which I have got, that is no longer applicable. Is it clear to you? So, therefore, for the fluid particle system, what we find for fluid particle system, as I have already shown you, that we can go till a particular point, beyond that it is not possible. So, therefore, this gives you the limit of the packed bed line, where at this particular point particles are just fluidized. Here particles are supported from below, here particles are supported, need to be supported from above. So, this is one particular point which I wanted you to remember, that for gas solid cases, since they are very flexible, for such flexible cases the curve can extend from alpha equal to 0 to alpha equals to 1. But for fluid particle cases, they cannot extend beyond the critical value of alpha, which gives you the maximum limit of solid packing. Beyond that, solid-solid interactions becomes important, and the basic assumptions based on which I had made the derivation is no longer valid. Okay. So, therefore, beyond that we cannot proceed. Now, this value of alpha critical, it depends upon the nature of the particles. If they are flocculating type, then it can be as low as 0.1, but generally it varies between 0.58 to 0.62. So, that we take alpha critical equals to 0.6 for most of the cases. Agreed? Now, certain other things regarding the graphical technique also I would like to mention. Now, the first thing which I have already mentioned is that how to construct the flooding line. Okay. So, that we had already mentioned. Now, there is, now if you want to denote the equation of the flooding line analytically, then how can we do it? Now, depending upon this particular line which I had got, this was J21, this was alpha. So, and this was the curve if I say, and maybe if we consider upflow, then this is the line. So, therefore, at any particular point you say alpha equals to alpha, here alpha equals to 0, is not it? Here J21 equals to J2, and here we have J21 equals to J21, correct? Now, what is the slope of this line? The slope of this line dJ21 at this particular point, dJ21 d alpha, this is nothing but J2 minus J21 by alpha minus 0, correct? This portion it is correct. Okay. Now, at the point of intersection, what do we know? We know at the point of intersection J21 equals to u infinity alpha into 1 minus alpha whole to the power n. So, at this particular point, if I differentiate J21 J alpha in terms of this, so what do I get? This is d alpha of u infinity alpha into 1 minus alpha whole to the power n. This equation, if I differentiate it with respect to alpha, then I get a slope of this curve, and this slope I can substitute it here, okay, and then I can get an analytical expression of relating J2 and J1 under conditions of flooding. So, if we perform this differentiation, what do we get? From this particular differentiation we get this is u infinity into 1 minus alpha whole to the power n minus u infinity alpha n into 1 minus alpha whole to the power n minus 1. Just simply I have differentiated this part. Okay. Now, moment I have got this, so from there I can get, if you substitute it here, then I get what is J2 equals to, it is u infinity alpha into 1 minus alpha whole to the power n minus u infinity 1 minus alpha whole to the power n plus u infinity. Any point if you do not understand, you tell me. This should come as J2, because from this particular equation we know J2 equals to, probably you cannot see it here, from this particular equation we know that J2 equals to J21 minus alpha dJ21 d alpha, is not it? From this equation we know this. Now, dJ21 d alpha I have already found it out, J21 I know it already. So, if I substitute this and if I substitute this in this particular equation, I get an expression of J2, where this can be written down as alpha square. If you just substitute, you will find out n into. So, J2 it can be obtained by an equation as alpha square u infinity n into 1 minus alpha whole to the power n minus 1, correct. Achha, similar way, what is J1 equals to? J1 equals to, we know that this from this particular graph, this is minus J1, isn't it? So, from here if we do, then here we know that minus J1 minus say J21, this will be alpha equals to 1, this is alpha equals to alpha. Okay. So, we can find out the slope from these 2 points, we can also find out the slope from these 2 points, isn't it. So, therefore, if we do that, let me draw it once more. This is alpha equals to 0, alpha equals to 1, this is the curve, this is the line. So, in this line this is alpha equals to 0, sorry, alpha equals to 1, this is alpha equals to 1 alpha, this is minus J1 and this is J21. So, what is the slope in this particular case? The slope will be minus J1 minus J21 by 1 minus alpha, this will be the slope dJ21 d alpha, correct. Again this dJ21 d alpha, this can be substituted from this particular equation. Okay. We can substitute this in here in dJ21 d alpha, and then accordingly we can find out the J1 under flooding conditions, or we can find out J1 J2 for the corresponding points in the curve. So, if we do it, then in this case what do we get? We get, just substitute it and you see that for what is the thing that you are going to get. This J1 it is nothing but minus of 1 minus alpha dJ21 d alpha minus J21, isn't it? Or this gives you, if you write it down, you get minus u infinity. Please perform all these your whatever derivations I am doing, please perform all these derivations in your home and to find out that whether you are getting the expressions. There can happen that I am making some mistakes. So, therefore, unless you do the derivations on your own, it is going to be very difficult. N u infinity alpha 1 minus alpha whole to the power n minus u infinity alpha into 1 minus. Please do them and check up that I have done the correct thing or not. It can always happen that I have made mistakes, or even I have made mistakes while I am doing it at the present moment. Okay. So, this gives you u infinity into 1 minus alpha whole to the power n into n alpha minus 1, or in other words this can be minus of 1 minus n alpha u infinity 1 minus alpha whole to the power n. So, therefore, what do we find? This is the J1 at flooding point and this is the J2 at flooding point. So, therefore, what are we required to do? We are required to locate this J2 and this J1 for different, see they are functions of just alpha n and u infinity. Okay. For both the cases, if you find, you will find that they are functions of alpha n and u infinity. So, therefore, n and u infinity they depend upon the flow patterns, interfacial distributions, they are going to be different for bubbly, slug, churn, etc., etc. So, for the corresponding flow pattern you find out n and u infinity. Okay. Then for each alpha you can find out J2, you can find out J1. Accordingly, for each alpha you can locate the endpoints of this particular curve, and then from there we can find out each and every point and we can construct this particular curve. Agreed? So, this was an analytical way of doing it. Okay. By this particular method you can locate this particular curve. Okay. Either this method can be used or the flooding data can be used. Got my point? Now, there is a second way of representing the data or the relationships which we have got. Same thing, we start from the same particular relationships, that from this particular equation itself we can start, and we can find out a relationship between J1 and J2, okay, and we can represent it in a curve of J1 versus J2. Now, let us see how to do it. This is simply a second way of representing the curve. Now, in this particular situation, what do we have? Let me minimize it and let me see if I have it or not. Yeah. So, this you do not see now, let me see. Now, what is the second way of representing it? Second way of representing it is, I have this equation J21 equals to J2 minus alpha j or minus alpha J1 plus J2, is not it? Or this can be written down as 1 minus alpha into J2 minus alpha into J1. Can I do this? Or in other words, I can write J2 equals to J2 1 by 1 minus alpha plus alpha by 1 minus alpha J1. Just I'll just rearrange it for my convenience. Now, if you see this particular equation, now this particular equation, if you notice, what do you find? That from the drift flux model, we can get a relationship between J2 and J1. Okay. Now, observe that for constant alpha, what sort of a curve do you expect between J2 and J1? It will be a straight line with the slope of alpha by 1 minus alpha, okay, and the intercept is going to be this. Okay. Now, you tell me, suppose we draw this, we draw the straight lines for different conditions. Let us take the straight line, let us see how it resembles. If we draw, this is J2, this is J1. Okay. J2 and J1, they can have different positive as well as negative values, is not it? Now, for a particular alpha, you tell me what will be the intercept here and what will be the intercept in the x axis. X axis means J2 equal to 0. Okay. So, when J2 equals to 0, what will be the intercept? Intercept for J2 equals to 0, or the intercept minus J2 1 by alpha. So, therefore, it is always going to be some sort of this intercept is going to be minus J2 1 by alpha. What will be the intercept on the y axis? J2 1 by 1 minus alpha. So, therefore, what are we going to get? We are going to get a straight line something of this sort. This is for one particular alpha. Okay. If we go for lower and lower alpha, we find that we get something of this sort. Again, we go for a higher alpha, we get something of this sort. In this particular way, our straight lines, we get different straight lines for different alpha values. Okay. Maybe this is for alpha equals to 0.1, this is for alpha equals to 0.9, and so on and so forth. So, I could not draw it very well. The thing is, if you draw it properly, maybe I will give you a problem in which you can draw it and you can find out that in this particular region where both J2 and J1 are positive, that means this is co-current upflow. always a solution is possible. Okay. In this particular region where both J2 and J1 are negative, that means this is co-current downflow. Here also you find that always a solution is possible. Okay. Here this one is J2 is positive, J1 is negative. Okay. So, therefore, J2 positive, J1 negative means it is counter current with gas up, J2 positive, liquid down. You will find that since I have not drawn it very well, but if you draw it, you will find that more or less you will find some sort of a limiting region where here solution is possible, beyond that solution is not possible, and this will be sort of a curve where this curve will be limited by the flooding line. Okay. And here it will be counter current with gas down, J2 is negative, J1 is positive and liquid is up. Here no solution is possible. Okay. This one I could not draw it very well, but if you draw it, then you will find that more or less all this for different alpha, they are going to coincide under different conditions. It will be sort of this more or less if you draw it. It will be something of this sort. Your for very low alpha, it is going to be something of this sort. For very high alpha, it is going to be something of then for lower cases you get something of this sort. So, more or less from these intersections you get a curve something of this sort, which is the flooding line, and you know that your limited operations will occur within this particular flooding line. Here you are always going to get a solution. This is J1, this is J2. Here you are always going to get a solution. Here you get a solution under limited conditions. Here you do not get any solution at all. Okay. So, this I have represented it in the form of a PPT, which I am going to show you. This particular PPT which tells you that in co-current upflow there is always a solution, in co-current downflow there is always a solution. If you plot the curves, we will be doing it when I give you more problems. You find that there is a limited region in counter current flow with gas up, liquid down. This limited region there is a solution, and beyond the flooding line there is no solution, and in this particular case you find that there is no solution for gas going down and liquid going up. So, therefore, in order to conclude this particular portion, what are the things that we have discussed? First thing I have discussed is the drift flux model, how to obtain the different mixture parameters with respect to the drift flux model. Definitely we had expressed alpha rho Tp in local velocities in terms of the drift flux model. We found in all the cases the expressions that we obtained, they were a function of J21 non-dimensionalized or normalized with the individual volumetric fluxes. For all the terms we had J21 by J2 or J21 by J, something of that sort. Okay. Now, if we have an independent method of finding out J21, it is going to be very advantageous. Normally, for the flow situations which we have, there is an independent way of evaluating J21. That particular method we took from the two fluid formulation. From the two fluid formulation, we found out that more or less J21 can be expressed in terms of certain governing parameters, and we found out that for steady state inertia dominant conditions where mutual hydrodynamic drag is important, more or less J21 can be a function of alpha only for a particular system, for a particular flow pattern. The functional form of J21 and alpha is going to be different for different flow patterns. So, accordingly, by studying the different flow patterns, a generalized expression was proposed where it had two parameters u infinity and n, which vary with the different flow parameters, different flow patterns. So, depending upon the flow pattern, a suitable u infinity and n had to be incorporated, and accordingly we could get a proper relationship between J21 and alpha for different flow patterns. That particular equation, it yielded a curve. So, we found the best way of finding out alpha and J21 was a graphical solution. So, we discussed the graphical solution and we found out that there is always a solution possible for co-current up and down flow. Two solutions possible till a critical particular flow conditions for counter current flow with gas up, liquid down, beyond which there is beyond the flooding point no solution is possible, and there is never a solution possible for counter current flow with gas down, liquid up. Then we discussed different ways of representing the data using the drift flux model. One was J21 versus alpha, the other was J2 versus J1, and finally what we did, we found out that generating the curve is not always very simple, and therefore, this curve can also be generated from flooding data, when the flooding data can be obtained from for different values of alpha. We can find out analytically the different values of J1 and J2. If we plot them, then we can generate the curve over the entire range of alpha from alpha equal to 0 to alpha equals to 1. Other point which has to be noted was that for fluid combinations, the curve can go from alpha equal to 0 to alpha equal to 1, but for fluid particle combinations, usually there is a discontinuity beyond a critical value of alpha, and when there is beyond the discontinuity, we find that the drift flux model under this condition is no longer applicable, because under that condition particle interactions become important. So, the basic equation has to be modified. Now, in the next class we are going to discuss how 2 and 3 dimensional effects can be incorporated in the model, how it can be made more generalized, and that will complete our drift flux model. Thank you very much.